Okay, so welcome to the next lecture, TA session on this particular NPTEL course, Applied Linear Algebra for Signal Processing, Data Analytics, and Machine Learning. So let me confirm one thing. Okay, cool. So basically, this is the 12th TA session for this course, and is also the TA session, the last regular TA session for this course. Okay, so this course is offered by Professor Aditya Jagannathan from IIT Kanpur. So a little bit about myself. So my name is Yashvanth, and I'm presently a PMRF Ph.D. research student at the Indian Institute of Science, Bangalore. And I'm advised by Professor Chandra Murthy, who is also with the Department of ECE at IISc Bangalore. My broad research interests lie in statistical signal processing and applications in wireless communications, while I currently focus on researching on algorithms and devising techniques for system design aspects on intelligent reflecting surfaces for 5G and beyond wireless communications. Excuse me. You can contact me at this particular email address, yashvanth.l@iisc.ac.in. And you can also write to me if you have any further details or queries about the course, or any conceptual queries to this part. I mean, you at this email ID, and you can know more about me through this particular web link. Okay, so today the topics that we'll be covering will be twofold. Firstly, we'll be looking at the weighted least squares, and also then we'll be looking at conditional Gaussian distribution for MMSE estimation. Okay, so this is basically the broad topics which Professor had covered in the week 12 lectures. So as usual, we will now first start the session by summarizing week 12 lectures. Okay, so in case any of you are having some problem in terms of not hearing me or something, please write on chat so that I can get know. Also write any queries that you may have on the chat. Okay, so part one is the summary of week 12 lectures. The first concept is weighted least squares. Okay, so what is okay? So to motivate weighted least squares, let's consider our general least square setup. Okay, so basically this was the problem that we had discussed in the earlier sessions, namely that I want to minimize the norm of the difference between y, which is the observation, and a times x, which is the transformed version of the original vector, which I'm interested to find out. Okay, I need to find such an x such that this norm, the L2 norm square of the difference between the vectors y and ax, is as minimum as possible. Okay, so we saw that the solution to this particular problem is equal to x hat is equal to a transpose a the whole inverse a transpose y, or it's also called a pseudo inverse times y, as long as this expression is valid, as long as a is full column rank matrix. Okay, so this was the simple least squares that we have been seeing till the last session. But what is weighted least squares? So how does that particular concept differ? So if you see this, the cost function of your least squares, so this I can rewrite the cost function as, so this is nothing but norm square, right? So this is nothing but inner product of y minus ax times it's with inner product of y minus ax with itself. That is y minus ax the whole transpose times y minus ax. Okay, so this is basically your uh, I mean, this is basically the cost function in of the original simple least squares. Fine. But now what is weighted least squares? So in between the two terms, y minus ax transpose and y minus ax, you introduce an additional matrix. Okay, introduce an additional matrix that is like the weight for the entire cost function. So this the x that minimizes this particular cost function is said to be the weighted least squares estimate. Okay, so basically if you can, in case some the special properties of w, generally it makes useful to have a w which is known as something called a positive semi-definite Hermitian matrices. This is also something we have discussed in the past. So basically a matrix A, it should be Hermitian matrix. Okay, okay, maybe I will note it, ink it up. Okay, so let me just write it down. So there's a matrix A. Okay, it's a square matrix C to the n by n, which is Hermitian. matrix A which is Hermitian, okay, is said to be or is positive semi-definite, or I will call that as PSD, if for every x, for any vector x you take in C to the n, x, the term, the product x Hermitian A times x should be greater than or equal to 0. Okay, any matrix which basically satisfies this condition is called as a positive semi-definite matrix. Okay, so so basically, and the interested matrix, why do we want this to be the, why do we impose the W matrix to be positive semi-definite? The very important reason being that, see, you can regard this y minus ax as some vector, let's say z. Okay, so basically the entire cost function I can write as z transpose wz. Okay, so I want the cost function to be, I want it to be only a positive number. See, because you see, here it is a norm square, right? A norm is always a positive number. So in some sense, I want to retain the cost function to have the same property similar to what the simple least square has. Okay, so I want this number should always be greater than or equal to 0. That is possible only if W is a P. I mean, one of the conditions, one of the sufficient conditions for this positivity is guaranteed if you take the W matrix to be a Hermitian positive semi-definite matrix. That's why generally in weighted least squares, the weight matrix turns out to be a positive semi-definite matrix. Okay, so for there's a property that professor had mentioned in the class. Any positive semi-definite Hermitian matrix admits something called the Cholesky decomposition. Okay, so for example, Cholesky decomposition, you can think of Cholesky decomposition to be like something like taking the square root of a matrix. That is, if I have a matrix W, I can write this as W square times 2, right? This also I can write it as, so see, if W is Hermitian, power half, that is square root of the matrix, is also Hermitian. Okay, so I can write this as W half into W half, or that is same as W half into W half transpose or Hermitian, whatever it is. So this is nothing but, if I call D is equal to W power half, this is nothing but D into D Hermitian. Okay, that is equal to W. This is exactly what I'm trying to say. Whenever there is a matrix which is positive semi-definite, you can find a square root of the matrix. Okay, and precisely the matrix D here, which is also called the Cholesky factor of the matrix W, is indeed the square root of the matrix W. Okay, for a simple reason that you have, when given W, D is nothing but W power half. That is like taking the square root of matrix. So it's called the square root of a matrix given by the Cholesky factor. Okay, so now what you can do is you can write this W as something like, D transpose times D. Okay, then you can write Z. This is nothing but Z transpose D times Z, which is same as taking the norm of dz del 2 norm of dz square. Correct. Now what is D? D is nothing but W power half, or W power half times its Hermitian. But anyways, W per half is a Hermitian matrix, so it doesn't matter whether you write D as W per half or W per half the whole Hermitian. Both are same. That is, by this way you can reach this particular step. Okay? It is nothing but the L2 norm square of W power half times y minus ax. It is not just y minus ax. Okay, the difference between weighted least squares cost function and the simple least square is that you have an additional matrix W here. Okay, that is coming as power half. Fine. So this W per half is called the Cholesky factor of W, or the square root matrix, or it is also the square root of W. Just to ensure that we are all on the same page, can you, is this clear till now? Can anyone confirm if it's clear till now?
I just joined now. I'm just following it. Maybe others can
Yeah,
wait.
yeah.
Please go
So, I
to
mean,
the lectures.
yeah. So basically, what I told is, I'll quickly repeat. So what I told is, in general least square, that is simple least square, what we have seen till last class or in previous session, is something of this form. I need to find x which minimizes this square of the two norm of the difference between y and ax. Correct. That is the simple least squares setup. And the solution to the x that solves this problem, minimizing the norm of y minus x is given by this vector A transpose A the whole inverse A transpose y. Okay, and that is again this expression is defined if A is full column rank. Only then can you define the inverse of the matrix A transpose A. But now what I'm introducing something called weighted least squares. What I'm saying is, so if you see this in simple least squares, the cost function is norm of y minus ax. You can write this norm as something like this, right? It's nothing but, I mean, any x L2 norm is nothing but x transpose x. Right? That's what I'm writing here. I'm writing that as y minus ax the whole transpose y minus ax. Now, what weighted least square does is you introduce an additional matrix in between matrix W. It's a matrix W, and that the cost function now becomes y minus ax the whole transpose W times y minus ax. Now, the x that satisfies, that minimizes this resultant cost function is said to be the weighted least square estimate of x. Okay, that is what I told, and I additionally told that in many of the cases it is meaningful to have the W as a positive semi-definite matrix only for Hermitian positive semi-definite matrix. The reason being that if you impose that constraint, the entire cost function is always a positive number because of the properties of positive semi-definite matrix. So, and essentially, if you incorporate this norm, this kind of a structure, you can write an equivalent norm, cost function in terms of norm, which is basically this particular number, L2 norm of W power half times y minus ax square. Okay, so instead of having just y minus ax L2 norm square, you have you have pre multiplied by the matrix W power half. That is the difference between a simple least square and weighted least squares. Okay, this is what I told. Okay, yeah. So again, now this is nothing but one can solve this particular least square setup, weighted least square scenario, and you can show that the optimal x, the weighted least square estimate, is given by this particular function, this particular expression, A transpose W times A the whole inverse A transpose WY. Okay, so basically, for example, as a sanity check, if I put W equal to I, that is the identity matrix, right? Then this boils down to our original expression A transpose A the whole inverse A transpose Y, which is same as our general least squares. Okay, now where do such kind of weighted least squares find applications? In something called, I've given an example, even professor had discussed this in the class. Estimating a DC signal from a uncorrelated, non-identical, noisy observation. I will explain it. Noisy observations. So basically what I'm trying to say is the given system is something like this. Okay, there is a DC signal that is A. It's a constant number. For example, A equal to 5. That's like a DC signal.
DC stands for direct.
Yeah, direct component, our AC and DC signal. Yeah, I'm saying DC because it doesn't vary with time. The signal A does not vary with time. It's just, let's say, fixed number, some number, say 5 for every time, all time. That's why I call this as DC signal. So now, for example, suppose I don't observe. I mean, I don't know what this DC value is. Okay, I observe. However, what I do is I observe this DC value in the presence of some noise as YI. For example, I have some sensors deployed everywhere. The sensor gives me a measurement output YI. Okay, so I ranges from 1 to m. You can think of I is like a ith time instant. Okay, so there are m time instants, and every time instant I get the observation Y1, Y2, and so on till Yn. And each time a different noise Ni get added to the actual desired signal of interest A. Okay. Further, I model how does these noise are modeled as? They are modeled as Gaussian noise. That is, they come from a Gaussian distribution whose mean is 0 and variance is sigma I squared. So variance basically measures the average power of the noise signal. So now you see here, I impose this particular constraint, that is sigma 1 not equal to sigma 2 not equal to, and so on until sigma m. Right. So basically what this says is the noise that get added at every time instant I will have different power levels. Okay, the average power of the noise that gets added to the measurement signal, measurement output at any time instant I will keep changing with time. That is, the power is not constant. The noise power is not constant across all the m measurements. Okay, now in this, if that is the scenario, okay, that is what I call it as, it's something called uncorrelated. What do you mean by uncorrelated? Means that, let's say, the noise that gets added the first time instant and there's a noise that gets added the second time instant, the noise components corresponding to the first and the second time instant will be independent of each other. They are normal. I mean, you cannot tell anything. Let's say, I mean, if the noise gets, let's say, noise at time instant 1 is n1, and let's say noise at time instant is n2, n1 and n2 get generated independently. There is no correlation among them. That's called uncorrelated. Why non-identical? Sorry, why non-identical? Only because the noise power that gets, the noise power of the noise at every time instant is different. That's why it's called non-identical. Okay, noisy observation, observation is nothing but yi. So given these m set of measurements yi, the goal is to estimate or find out what is the DC signal A. Okay, so that is basically the setting. Now, why? Now the thing is, see, for example, if the noise power at the first time instant is, let's say, zero point 0.5, okay, zero point 0.5 watt power. Let's say that the second time instant is 1 watt. What does it mean? That means in the second time instant, the noise that got added was very, very high. But first time instant, the noise that got added was very small. That means this first time instant has a better, it has a very smaller noise compared to second time instant. So I would tend to give more weightage to y1 in order to estimate what A is compared to y2, because y2 is having more noise, right? Because the noise power is more in y2 compared to y1. That's why what I do is I first do something called what do I do is in my estimation of my I do a weighted d square. That is, I weight every component of yi depending on the noise variance that gets added at that particular instant I. Okay, so specifically what I do is I define something called R inverse as something like this. It's a diagonal matrix having the inverse of noise variances at all the time instants from cap 1 to capital M. That is R inverse. And this is nothing but the data itself. So there's nothing but y1 equal to A, y2 is also, this is something the same as class formulation as done in the class. Okay, then you define and then you get the optimal A hat, okay, to be something of this form. So what does it say? That is, the estimate of your DC signal is something given by the ratio of two quantities. Now very clearly see the numerator. What does it do? It just doesn't do summation over yi. No, it doesn't do that. It does something like summation over yi divided by sigma I square. Okay, so what does it do? So whenever the noise variance is very high, then this yi divided by sigma I square will be very small. So in finding the estimate of A hat, I give small weightage or less weightage to those observations which are corrupted by noise having large noise power. That is exactly what this particular numerator does. Whenever sigma is very, very small, that is, the noise power is very small, meaning that only small noise get added to the measurement, your yi by sigma I square will be large. That adds better to the contribution to the estimation of A hat. That is basically the physical, interpretation behind this expression. And again, this denominator is independent of yi, so it gets this. This is only for normalization factor, because you need to undo the effect of what you have done in the numerator. Okay, your noise, this particular A hat should not be a biased estimate of DC depending on noise power. It should be an unbiased estimator. That's why you introduce this normalization factor. Okay, this is precisely the conditions where you introduce, for example, weighted least squares, because precisely the weights are the noise variances. Okay, this is an example of weighted least squares. Now the next topic that was discussed was on matrix inversion lemma. So if you ask me frankly, what are the applications? there are very good number of applications, especially from an implementation viewpoint. Because typically, if I want to, let me just give you a fact, a number, okay? Okay, let's say there's a matrix A, which is of size C to the m by m. It's a m-dimensional matrix. Let's say it is invertible. Okay. Now, if I want to find the A inverse, okay, it consumes the complexity of finding the A inverse. Complexity means, what I mean is, see, if I want to compute the inverse of a matrix, I essentially feed all the values, or I feed the matrix entries to some computer. The computer will return me back the inverse of the matrix, right? The computer in turn will do some calculation. It will do some series of multiplications and additions. Uh, the complexity involved in that party, that is the roughly the number of additions and multiplications scales as O of m cube. Okay, forget about O. O stands for order of. Okay, it's just a standard terminology. So for an m by m matrix, you would roughly need m cube number of additions and multiplications to compute A inverse. So for example, imagine I take a 10 by 10 matrix. Then that means roughly I need 1,000 multiplications and additions in order to compute the matrix A inverse. It's a huge computationally complex task, right? But suppose, can I somehow reduce this complexity? There are many methods, and one such method is matrix inversion lemma. Okay, so the matrix inversion lemma is given by this particular expression, where it basically tells, when I add a matrix A with some other matrix, say it's a product in its product term UCV, and if you want to compute the whole inverse, what is this inverse in terms of just the A inverse alone? Okay, there's nothing but A inverse minus some other matrix. Now, suppose, when is this matrix inversion lemma useful? When the knowledge of A inverse is already known, or A inverse is easy to compute. See, I'm saying there's a why am I interested in this? Because if A inverse is easy to compute, this first term is easy to compute, this term is easy to compute. Maybe, yeah, there's a question whether is this easy to compute. Let's see. A inverse is easy to compute. So when A inverse is easy to compute, or A inverse already known, computation of RHS is very, very easy. But computation of LHS is non-trivial. Even if A is known, A inverse is known, there's no use. You still need to figure out what A plus UCV in UCVs, and then do a whole full-fledged inverse operation. Right? So this is the reason by basically you would need to have an expression which basically updates the inverse as the matrix gets changed. Okay. So, and especially, let's say, suppose, assume that this matrix is easily invertible, then RHS is easily invertible. Okay, so that's why this particular matrix inversion lemma is very easy, very useful whenever A inverse is easy to compute, or when A inverse is already known to you. And this particular computation, the middle inverse matrix, because this is again an inverse, right? This inverse is little easy to compute. One very simple example, very simple. This is also, yeah, someone pointed out. This is also called the Woodbury's identity. Okay. Excuse me. Okay, so now an example of where you find utilities of such matrices. For example, if I have a matrix, let's say I, okay, I add another rank one matrix, X transpose. You can show that there's a rank one matrix. That's why it's called rank one update, or rank one. I would, rather than saying update, I would say rank one perturbation. So this perturbation means you disturb your matrix. Your original matrix is I. Now I'm disturbing the matrix I by some other small low rank matrix X transpose. That is, I'm disturbing by rank one matrix. That's why it's called a rank one perturbation. Now, if someone asks you to find the inverse of this rank one matrix, inverse of the rank one matrix added with the identity matrix. So then you should manually compute all the entries of the matrix I plus XX transpose, and then you need to do a full-fledged inverse operation, right? Right. For example, I'll give you an example number. Let your identity matrix be of size 10. Okay, so then this is by 10 cross 1, and this is 1 cross 10. So totally it's a 10 by 10 matrix. So inverse would need, therefore, inverse needs 1,000 operations. Okay, if I were to do my LHS, I would need 1,000 operations. Let's see how many operations I would have. I would have saved if I had opted matrix inversion lemma and performed the RHS operation. So by matrix inversion lemma, you can show that this inverse is same as computing this number. Okay, so how many operations is this number? See here how many that it's a XX transpose. This is a 10 by 1 matrix. This is a 1 cross. It's a 10 by 1 vector. It's a 1 cross 10 vector. The total number of operations involved is 10. Okay, or 100, maybe 100. Okay, total number of because it's a 100 by 100 matrix, you need to compute each element. So sorry, it's a 10 by 10 matrix. You need to compute the value of each element. There are 100 such elements, so the total number of operations is 100. Now this is a norm of x. There are 10 elements, so you need to compute 10 such values and add them up. So it will be of the order 10 elements. 10. Okay, 10 operation is 10 plus 1. It's again like of order 10. So now there's a division that is like just one operation, and then there's a subtraction that is again like there are, see, this is a 10 by 10 matrix. So you need to do 10. You need to do some approximately only 10 minuses, right? So totally, if you see, totally you will end up in having a number of calculations approximately 120. See, I have saved by 880 calculations rather than performing 1000 operations. Okay, so that is the usefulness of such kind of numerical results. One such numerical result is Woodbury identity or matrix inversion lemma. Okay, so in the class, Professor had also proved why is this how was this Woodbury identity make sense. He also gave a proof. Okay, the next topic of this week was on conditional Gaussian random vectors. Let's say there is a vector h that we are interested to estimate. Oops, sorry. There's a vector h that we are interested to. It's a parameter that we want to estimate, meaning that I want to know what is the value of the vector, each entry in the vector h. But I know a priori. I know there's a prior information about this particular vector, namely that each element, this particular vector, is a Gaussian vector with zero mean and covariance matrix RH. Okay, meaning what? Basically every element is a Gaussian random variable, and you have appropriate variance and appropriate correlation coefficient between any two entries of the vector h. Okay, this is the parameter I want to estimate, but I don't know. No one revealed me the actual values of h, which I'm supposed to estimate. But now let's say there is another vector y. Okay, let's say this original parameter h is of dimension m cross 1, meaning that it's an m length vector. Let's say there's another vector y, which is also a Gaussian vector with zero mean and covariance matrix ry. Okay, let's say it's an n by 1 vector. Okay, and someone tells that h and y are jointly Gaussian. What do you mean by jointly Gaussian? I mean, one way to define jointly Gaussian is if you write down the joint PDF of h and y, you get a particular structure. I think this was introduced before in the class itself. I think third or fourth lecture. Okay, that is, you can refer what joint Gaussian is. Now, if these three conditions are satisfied, namely that h is a Gaussian vector, y is a Gaussian vector, and someone told you that h and y are jointly Gaussian, okay, then the question is, what is the conditional density of h given y? That is, if someone told you, okay, the exact value of every entry of the vector y, then what is the probability, that what is the likelihood of occurrence of a particular number in every entry of h? Okay, for example, okay, you can relate it like this. Suppose I threw a die. Okay, so if someone had told you no information about it, then what you may think is, okay, one of the 6 phases will appear. Okay, let's say I throw a die and I just close my eye, and one of my friends has seen the die and he told, look, okay, now it's an even number. So now our our uncertainty is now reduced, because earlier our uncertainty was that it could be one among 1, 2, 3, 4, 5, 6. But once my friend has told me that it is one among the even numbers, I still don't know what is the exact number, but I know the information. Someone has told me that it is one among the even numbers. Now the uncertainty has gone down because the value is one among 2, 4, and 6. It cannot be 1, 3, and 5. Right? That is called the conditional event. Here I'm conditioning. I observe what my y is. After observing what my y is, what is the density? What is the distribution of the vector h? Okay, that is called conditional density. Density is also, the word that we use to describe the probability distribution. Okay, there's a small difference between density and distribution in the sense that mathematically, if you take the derivative of distribution, you get density. But roughly, density tells you what is the likelihood that a particular number will occur, uh, will be realized by a given random variable. Okay, that is precisely what is the conditional density, that is f of h given y of the realization y h comma y. Okay, you can show that one fact I will tell you right away, that the fact is that if h and y are Gaussian vectors, not just that, they are also jointly Gaussian, then this conditional density is also a Gaussian vector. Okay, that is the fact you can take away. You can actually prove it, but you can just take it on faith. Okay, now we know that a Gaussian density is just described by two parameters, mean and covariance. So if I find out the mean and covariance, the conditional mean and conditional covariance of this density distribution f of h given y, then I know what is the PDF of f of h given y, because for Gaussian distribution only these two parameters are needed. Once you know these parameters, you can write down the expression for the Gaussian PDF expression, or the probability density function expression. So for that, professor had spent two classes on deriving the conditional mean of this random variable. So let's say random variable z is defined as h given y. So sorry, not z. Let's some other random variable. Let's say a is equal to h given y. Okay. Then professor spent one class on deriving the conditional mean of a. That is, what is the expected value of a. That is, what is the expected value of h given y. And in the next class, professor spent time on understanding what is the expected covariance, okay, of h given y. So to that end, he made use of this particular trick. We define the random variable random vector z is equal to h minus this particular number rhy times ry inverse times y. First, he proved that, and then take a given y on both sides, and then take expectation. Okay, that is basically this equation. In class, he proved that this term will go to 0. And this term, so given y, what is the average term? So then someone told you that this is what has happened. There is no meaning of averaging over it. If someone told that y has happened, then the average of y is nothing but same as y itself. Okay, that's where expected value of y given y is same as expected value of y given y is same as y. It is not expected value of y. No, if y conditional that y is equal to this, the only average over all such y is nothing but just the number whatever you've conditioned on. That's why just y. Okay, and now you can show equal 0. Bring this right hand this to the left hand side. You get this expression. Okay, so this is conditional expectation of h given y. Now conditional covariance. Similarly, first professor proved that conditional covariance of z given y, where z is defined as this particular expression, random vector. Professor derived that covariance of z given y is same as covariance of z. That's because z and y are independent. Okay. Now next professor proved. So now what happens? So covariance of z is same as covariance of z given y. But now z has its own expansion, h minus this r blah blah times y. That is basically this particular expression given y, because this is the given y here, it just goes over here. Okay. So now so given y, so what is important is given y. So someone told you what is the value of y is. This guy is no more random. This is a deterministic quantity because rhy, ry are all deterministic numbers. But y is now deterministic because you've conditioned on y. So this is a deterministic quantity. The entire second term is a deterministic quantity. So we know that adding a deterministic quantity will not change the covariance, or in other words, covariance of a deterministic quantity is 0. Right? Because variance means what? What is the random deviation? But with the deterministic number, there's nothing random about it. So there's no deviation. So the variance is 0. Right? So then this is same as covariance of h given y, which is what we want to find. See here, because this is what we wanted to find. H given y. We want to find the covariance of h given y. Right? So that is essentially captured by this particular expression, covariance of h given y. But now someone I know that is same as covariance of Z. And professor proved the covariance of Z is given by this particular expression. Fine. So now we have found out the conditional mean of this random variable A is equal to H given the Y. And we have found out expected value of A given Y or H given Y. And we have found out the covariance of H given Y. We have found out these two quantities. But now I know that it's a Gaussian distribution. So I can fully characterize this, the conditional density H given Y, which is complex, which is the Gaussian distribution with mean equal to the conditional mean, namely this particular quantity, and the covariance given by this particular quantity. Fine. This is this particular quantity, and this is your mean, conditional mean. It's very important. It's a conditional mean. Okay. So that was about conditional distribution. And then professor also delved into understanding, giving a connection of the conditional distribution with MMSE estimation. So for example, if I have a vector, for example, consider a scalar H. Okay, as there's a scalar H, I want to estimate via the MMSE principle. Okay, then basically the cost function of MMSE is nothing but this guy. Expected value of, so this is basically Y is basically observation, and there's a matrix A that basically gives a transformation matrix. So something like Y is equal to AH plus W. If this is your model, let's say someone told you what is the value of Y, you need to find what is H. Okay, then your MMSE will be something like this. Correct? Now modulus of Y minus AH square. In outside you take the expectation. This is why it's called. So this is called squared error. And this H is the expected with the expectation. It's called mean square error. Okay, this is okay. This is not max. This is min. Okay. Okay. So this guy is called mean square error, and the entire thing is called minimum mean square error or the MMSE. And the H hat is the MMSE estimate of H. Okay. It turns out that this H hat, the solution to this is an optimization problem. I want to minimize something, right? It turns out the solution for this MMSE estimation is nothing but the conditional expectation of H given Y. That is basically the numerator term is the variable which you want to estimate. So here I want to estimate H, so I have H given the observation Y. Okay, because Y is something that I observe. So that is basically your expectation of the variable which you want to estimate given the observation. That is how you define the conditional mean. It turns out that your optimal MMSE estimate H hat is nothing but the conditional mean of H given Y. Okay, so to illustrate it more in linear models with multiple measurements, this is what again I think done by professor in the class. Yes. Okay, so I have a scalar H which I want to estimate. Okay, there's a measurement. There's something like A that I showed in the previous example. It multiplies with some vector X. Okay, I take n observations in Y, which is an n by 1 matrix, and V is a noise. Okay. So here V is a Gaussian random vector. That is, I assume that the noise comes from a Gaussian distribution. Furthermore, what is very important? See, that's very, very important. I say that H is unknown, but okay, H could be determinacy. That is, it's a constant which is unknown, right? But what I do is, this is very, very important. In the framework of MMSE, what I assume is H is a random variable. I impose, that's called the prior distribution. Okay, this is basic. The H is something that is unknown to me. So what I do is I impose a distribution on H with an appropriate mean and variance. Okay, it turns out that theoretically you can prove that assuming H to be a random variable, a random parameter, compared to a deterministic unknown parameter, will help you in better estimating the value of H. I mean, better means what? The incurred error in estimation can be shown to be smaller if I had modeled my unknown parameter H as a random parameter than a deterministic parameter. Okay, you can show that. That is the entire principle behind MMSE also. MMSE assumes that the parameter that you're trying to estimate has a distribution, that is, it has a probability distribution. Okay, and precisely I assume a Gaussian distribution. It's a Gaussian random variable. Okay, so now then the question is, what is the what is the estimate of H? So MMSE estimate of H, simple. It's just the conditional expectation of the parameter that you want to estimate, that is H, given all the observations point. Okay, so now professor had derived in the class the optimal expression for H hat. Okay, and yeah, that is it. You can also, so this part, if you see this, there's an inversion here. You can use further matrix inversion lemma, for example, the rank 1 perturbation that I showed before. You can further simplify it something like this. Okay, so H hat MMSE is equal to something of this form. Okay, so very important to understand. Okay, I understand it's a little dense expression, but it gives a lot of insights. The first term is called the ML estimate of H. See, if you want to estimate a particular parameter, it does not I mean, it's not necessary that you should only find MMSE estimate. You can define your own cost function of your own interest. You can define the cost function in whichever way you want. Okay, depending on the engineering application that you have. And depending on that, you will get different estimates of H. Okay, one such principle to obtain the estimate of a variable which is not known as MMSE. Another such method to estimate your H is called ML estimate, or it's also called the maximum likelihood estimate. Okay, it does not take this ML estimate does not take into account that your H is a random parameter. It assumes that your H is a deterministic parameter. Okay, so, and depending, if H were deterministic, then what is the estimate of H? That is basically given by this expression. Okay, but if your H is a random parameter with some mean and variance, and if I'm interested in MMSE, then this entire expression is a estimate of H. Okay, so what is very important to see is, suppose if I impose a prior on H with this is sigma square H is something but the prior variance, the variance of H, which is basically the variance of the prior distribution that I impose on the unknown variable H. If that prior is much smaller than sigma square, which is the noise variance, then your MMSE estimate will tend to mu H, which is the prior estimate. That is the mean of the prior distribution which I'm imposing on the variable H. That's intuitive, because what happens if sigma square is very large? What does it mean? That means all your noisy observations are heavily corrupted by noise. Your YIs are heavily corrupted by noise, which means it basically suppresses the signal power in the power of the desired signal in YI. It suppresses. That means the estimator will tend towards the prior estimate, that is the assumed mean of the random variable H. On the other hand, if this quantity holds true, that is your sigma square H is much larger than sigma square divided by norm of X square, that means the noise variance is very small compared to the variance of the prior distribution, then the MMSE estimate will tend to this X transpose Y divided by mod norm of X square, that is the ML estimate. So basically this, so what can you see from this? Very important. MMSE estimate can also subsume ML estimate under one special case. The ML estimate is a special case of MMSE estimate. That's why MMSE is more superior. Okay, especially ML estimates will become very poor when you have the noise to be very high. On the other hand, MMSE can even tackle that by making your estimate to a prior estimate. Okay, and precisely that's what is given in this expression of analyzing the error variance. That is, so any estimation will come with an error, right? Associated error in estimation. Okay, if you now assume, if I do the estimation using an MMSE approach and if I write down the resultant error incurred in estimation of H, then this is the expression for MMSE. Okay, you see, this is nothing but the combination of both the prior variance and the variance due to the MSE, that is the error due to ML estimate. Okay, so it's a combination of both. If this guy is very bad, okay, this guy can still bring down the entire MSE down. If the first term is very bad, still the second term can bring the MMSE down. So MMSE is an optimal way to trade off between both ML and the prior estimations. Okay, so that was about the this week's lecture. Now let's move on to some problems. Okay. Okay. So first question goes as follows. Suppose I have a data set. Data set means I have a collection of all some many points, collection of data. Okay. X equal to x1, x2, xn, where basically every xi is an n-dimensional point. Okay, such that everything is random. It's a random point, right? Every time you choose a point, it could be different number. It need not be the same points. Such that the expected value of every point, any point, is 0. That is every data vector. So every x1, x2, and 1, xn, each element is a vector. Okay, and further it's a 0 mean vector. That's what expectation of xi is equal to 0, and the variance, the covariance, C defined as expected value of x minus mu xi times. Sorry, let me assume for moment I will assume that everything comes from complex field, no problem. X minus mu xi Hermitian. Okay, this C is given to be is a non-diagonal matrix. So what does it mean by non-diagonal matrix? That is C. That is basically what does it mean? That is elements of any random vector xi are correlated. Correlated. That means if I know, let's say first element, let's say x1 is a vector, right? So this will have, let's say x11, x12, and so on till x1n, right? Suppose someone told you the value of x11, then you can predict the value of x12. That is, knowing the information of x11 can help you in predicting or estimating the value of x12. That is basically the correlative nature of these two random variables. So essentially, if your matrix C is a non-diagonal matrix, that is, off-diagonal elements are non-zero, then that means the elements of any random vector. So this is a random vector, this is a random vector. Take any random vector, the elements among the entries of that random vector will be correlated to each other. Okay, that is the meaning of having a non-diagonal covariance matrix C. Now the question is, find an operator W is a matrix, okay, W with a size n by n, such that capital N by capital N, such that when applied over this data set, the output random vectors become or contain uncorrelated entries. Uncorrelated entries. Okay, so the scenario is like this. What I'm essentially asking is a xi, okay, you pass that to some W. Okay, this xi is basically the data set that we have in hand. Okay, this is basically different vectors. Okay, so and the expectation of xi Hermitian, because you see mu xi is basically 0. See, this guy is 0, so this guy will be 0, and this guy will also be 0. So this guy simplifies to expected version of xi into xi Hermitian. So C is nothing but xi expected value of xi Hermitian. So the given scenario is something is you have a set of all input data points xi such that their covariances are non-diagonal. Okay, I pass these vectors through a black box. Let's say, for example, that is denoted by an operator W, matrix W, and the output of this box is yi. Okay, such that if I now take the expected value of yi Hermitian, that is the covariance, is now becomes a diagonal matrix. Okay, so basically, I'm doing this is also called as whitening of a random process or random vector. Okay, collection of random vectors, infinite collection of random vectors will make a random process. That's why I told random process. But at a given time instant, I just pass one random vector to a black box, I get the output. So that's like a whitening of random vector. Why is it called whitening? Whitening because if I uncorrelate the entries of the entries in a given random vector, that is called whitening. Because so a simple fact, so for example, white means it has no response in a particular direction, right? So the term whitening derives from the nature of the fact that the signal is um, it is flat. For example, whitening means the if so basically what is it? Okay, let me put it this way. So basically, whitening of random vector, what it does is it will basically give you an autocorrelation function. If you write down the correlation function, that is only a delta term. That is, for example, if I write expectation of xi Hermitian or xi xj. Okay, let me take random variables, not vectors. So x y, okay, equal to 0 if x not equal to y, equal to sigma x square if x equal to y. Okay, x not equal to y and if x equal to y. Fine. So this you can compactly write it as expected value of xy equal to sigma square times delta of x minus y. So so basically, see, this is nothing but uncorrelated nature. So if x and y are uncorrelated and 0 mean random variables, then expected value of x times y will be equal to 0 unless x is equal to y itself. Okay, you can write this compactly as this notation. Now, if you define the Fourier transform of this delta function, what is the Fourier transform of delta function? It's a flat in frequency domain, omega axis, x of omega. It's flat, similar to a white light, right? White light is basically combination of several light colors. White color is combination of several colors, and white does not have. So basically, every color has its own frequency, right? And white is a combination of all these frequencies. So the basically the amplitude of the white light in any frequency is going to be roughly the same, right? So basically, generating an uncorrelated set of random variables means that these random variables in frequency domain, if you plot them, it will be something like a flat spectrum, like a white signal. That's why this is called whitening of a random vector. So basically, whitening of a vector means I'm basically converting this random vector into another random vector where the entries of the resultant random vector will be uncorrelated with each other. That is called whitening. It's a white signal. And that is how this particular process of converting a correlated data set to uncorrelated data set as whitening of a vector came about. This is just a side point, but my question is more than that. My question is, what operator should you choose so that this particular operation is accomplished? Converting a non-diagonal covariance matrix, that is correlated entries, into another vector where the entries become uncorrelated or the covariance matrix is a diagonal matrix. Okay, anyone has any thought? Okay, so let me then go ahead with this. Okay, let me tell you the solution. So let's recall what is the input covariance matrix. C is equal to expected value of X Hermitian. Okay. Now the fact number one that you need to observe is C is Hermitian matrix. Why? Very simple. Take C Hermitian, which is nothing but expected value of X Hermitian, the whole Hermitian. Which is nothing but expected value of X Hermitian, the whole Hermitian. Which is nothing but take the Hermitian, reverse property, X Hermitian, the whole Hermitian times X Hermitian. This is nothing but expected value of X Hermitian. This is nothing but C itself. That means C Hermitian equal to C, therefore C is Hermitian. Okay, so very important takeaway, any covariance matrix is a Hermitian matrix. Fact number two. Okay, fact number two is C is a positive semi-definite matrix. Why? Let's see. Take any vector, take any A in C to the n except zero vector. Okay, then A Hermitian CA is nothing but A Hermitian expected value of XX Hermitian times A. Since A is a random number, is a deterministic vector, you can just push A inside the expectation operator. This is nothing but expected value of A Hermitian X into X Hermitian A. Fine. Then there's nothing but expected value of A Hermitian X times A Hermitian X conjugate. But what is this? It's same as expected value of mod of A Hermitian X square. But see, this is always a positive number. Why? Because this is always a positive number. So if you take the average of all positive numbers, it cannot become a negative number suddenly. So if you take the average of all positive numbers, the resultant should also be a positive number. So that means A Hermitian CA is always greater than or equal to 0 for any A in C to the n except the zero vector. If it's 0, then you'll get equal to 0. That's only. I mean, no need of a except zero vector. You can include zero vector also, no problem. If you have A equal to 0, then basically A Hermitian CA will be equal to 0. That's all. Okay. Therefore, this is the defining property of a positive semi-definite Hermitian matrix. We already know that C is a Hermitian matrix from fact 1. So that means C is Ph.D. Okay. Now, since C is Ph.D, it admits a Cholesky decomposition. Okay, decomp. Okay, let's say C power half. That is square root matrix. Okay, that is basically what I'm saying is the matrix C can be written as C power half into C power half Hermitian. But C power half is also Hermitian matrix. Since C power half is also Hermitian, you can write this as C power half into C power half, which is same as C. Fine. So now, please pay proper attention. Define yi equal to C power minus half. That is basically you take the inverse of the Cholesky factor, or I'll say half, the whole power half times xi. I equal to 1 to capital N. See, remember, let me recollect the dimension. This is an n by 1 vector. This is an n by n matrix. This is an n by 1 vector. Now, so basically, these are the resultant data points xi. Okay, I have pre-multiplied every data vector xi by this n by n matrix C power half. That is the Cholesky factor of the matrix C. The whole inverse. That is the inverse of the Cholesky factor of the matrix C. I have pre-multiplied by that matrix, and I obtain the resultant vector yi. Okay. Now let me analyze a fact. Let me analyze a fact or a property. Cy, nothing but expected value of yi Hermitian. That is nothing but, sorry, Cy generally is nothing but expected value of mu yi minus mu yi times yi minus mu yi Hermitian. Now let's find mu yi first. Remember expected value of yi. That is same as expected value of C half inverse xi, but C half inverse is a deterministic matrix. It's a deterministic matrix. So randomness is only associated with the vector xi. So the same as take it out of expectation operator. This is the expected value of xi, but expected value of xi. You see the question. It says such that expected value of xi is 0. So this guy becomes basically c power minus half times 0 equal to 0. Okay, so basically your implies your cy is simply expected value of yi Hermitian. Now let's put the value of yi. What is yi? Expected value of c half inverse times xi into c half inverse times xi the whole Hermitian. Okay, but this is same as expected value of c power minus half into xi Hermitian into c power minus half power Hermitian. But since c power half or c power minus half is both are Hermitian matrices, this is same as saying expected value of c power minus half into xi Hermitian into c power minus half. But c power halves are c power half the deterministic matrices, so pull that out of the expectation operators. This is nothing but c power minus half of expected value of xi Hermitian times c power minus half. But what is the expectation of c xi Hermitian? That is precisely my c. That is precisely my c matrix. Okay, so this is nothing but c power minus half times c power minus half. But since c is a Ph.D matrix, it is also the same as c power minus half into c power half into c power half into c power minus half. This is because c is Ph.D. Now this will become identity. This will become identity. The whole will become identity, which is the diagonal matrix. Okay, so now please tell me what is the operator W that I need to choose so that given any input data vector xi, the output data vector yi will be such that the covariance of yi, covariance matrix of the vector yi will be a diagonal matrix. Can you tell me what is operator W? Yes. Yes, can anyone tell me? So the hint lies here. Yeah, so just see here. So essentially, every input should get multiplied by this pre-matrix and the output will be given. So exactly you need to apply this weight or this operator. Okay, so your W operator must be C power minus half. Okay, so this will is also called the whitening matrix, where C is the covariance matrix of the input data vector. Remember, so the if the covariance of input data vector is C, then C power minus half will be the whitening matrix. That is, if you pass this set of data vectors through the weight of operator C power minus half, the output will be a diagonal matrix. Not it's an identity matrix. In fact, that is, every element will have equal average power with uncorrelated nature among them. Okay, so that was the first question. Now the second question is a very similar counterpart. Okay, now let's see whether you should be able to tell the second question very easily. Okay, it's basically the converse. Now consider the data set. Okay, x equal to x1, x2 and so on till xn, okay, such that every data point is a zero mean random vector. Okay, but what is now is and Cx, which is autocovariance matrix of x, expected value of xi Hermitian is equal to identity matrix. That is now basically the input data point. The data point are such that the covariance matrix identity matrix. That is, they're all uncorrelated. That is, elements are uncorrelated. Uncorrelated. Now the question is, find an operator okay, to introduce a correlation in xi's, that is the input data vectors which are previously uncorrelated. You need to introduce some correlation in these vectors xi's so that the resultant output random vectors have a covariance matrix R. Okay, so I see the answer in the question, but I would like you to think a little bit. See, I want the output covariance matrix to be R. Okay, R, not anything else. So imagine it. So basically, there's nothing but the converse of the previous question, namely that now I have an input data set which is such that every vector has uncorrelated entries. Now, how do I introduce correlation among the entries of the data set so that basically what I do is I pass these vectors through an operator, let's say a filter or W, similar to this block diagram. Okay, so the output data vector yi will have correlated entries, and exactly the correlation, how much correlation should you introduce, that is dictated by the entry of the matrix R. Okay, that is xi. It is such that Cx, the covariance matrix identity, will be passed through a weight or an operator, which we need to determine what is that. Okay, and that will give you yi such that Cy will be equal to R. Okay, so now, going by the principles of the previous question solution, what you do is you define, let the W be R power half. Okay, be the Cholesky factor of R. Okay, then define yi equal to R power half times xi. Okay, now check. Okay, what is Cy is nothing but expected value of yi Hermitian. It's nothing but expected value of R power half xi into R power half xi Hermitian, which is same as expected value of R power half into xi power xi Hermitian times R power Hermitian by 2. But since R is again R power half is again a Hermitian matrix, it is the same as expected value of R power half into xi Hermitian into R power half. But R is a deterministic matrix, so pull that out of the expectation operator. It's the same as R power half into expected value of xi Hermitian into R power half, which is same as R power half into Cx into R power half. But what is Cx? It's same as identity matrix, right? This is nothing but R power half into identity into R power half, which is same as R, because you're multiplying R power half twice. So this is the resultant is R. So what is R? Cy. Cy equal to R, which is really the desired thing. Therefore, which is desired. W equal to R power half is the desired operator. Okay, so the chart I see C to the power half. Yes, C power half is correct if C is a desired covariance matrix. Here R is what I want to be desired, so R power half is the desired operator through which you need to pass your inputs so that the output data point or data vectors have correlated entries such that the covariance matrix of yi equal to R. Okay, fine. So, in fact, I want to point one more. The question one, where you're basically uncorrelating data. The question two is about converting uncorrelated to correlated nature. Question one is you have correlated nature already. So see here, you already have correlated sources, non-diagonal elements. You're converting non-diagonal to a diagonal matrix. It's called whitening, converting correlated to uncorrelated data. It's called whitening. This is very, very important because, for example, machine learning applications like PCA essentially does whitening. It basically requires whitened data. Requires whitened data points. That is basically you have to. It requires uncorrelated data. It basically, I mean, it not requires uncorrelated. It basically it does uncorrelation of data. I would say it does not requires it. Does whitening of data. Once you have uncorrelated the data points, that is precisely where you are able to separate it out into different components, and you take the eigenvector corresponding to the dominant eigenvalue, the principal component. That is the ideology behind principal component analysis. It just uncorrelates the data points. Okay, so this is a good point to pause for some time. So we can, this is 7:16 now. Let's meet back at 7:22. Okay, let's give some 5-6 minute break, and we'll meet back at 7:22. Okay, let's begin. I see a chart question. If if eigenvalues are negative, we cannot get singular values. Well, not really. So basically, singular values are always positive. Okay, for example, if you see there's something called negative definite matrices among the class of Hermitian matrices. All the eigenvalues are strictly negative. But if you see their singular values, you can still define singular values for them. So um, I did not really see the question. So it's possible that you can have eigenvalues negative and still you can get singular values. Okay, so let's move on. Okay, so next question is on weighted least squares. So basically, the way I view this question is transforming weighted least squares into simple least squares. Is it possible to basically transform your weighted least squares to simple least squares problems? Simple least squares is the same as general least square, which I described in the starting of the session. Okay. Okay. So the question is as follows. So suppose y equal to ax plus n is given. And so basically x is your variable that you want to estimate, and your n is basically um, um, the noise. Okay, so here noise vector is such that the expected value of n equals 0, while the expected value of n and Hermitian, which is basically the covariance matrix Cn, is such that Cn is not identity matrix, or it's not even a diagonal matrix. It's not even a diagonal matrix. That is basically I'm saying that um, um, uh, that the entries are the entries of the vector n are correlated. Also, the variances can be very different. That is basically the one of the problems that we saw before. That is basically noise variances across time instants were different. Okay. The question is now. Question is obtain a simple least square estimate of x in a transformed domain. Of x in the transformed domain. In a transformed, you need to identify in which domain should you transform, so that in that domain your your correlated nature will become uncorrelated, and in that domain your simple least square is sufficient. You don't require weighted least square. Transformed. Yes, given the fact that we have solved first two problems, you should be able to tell what transformation should I do on y, so that a simple least square solution is enough. You don't need a weighted least square. So first understand why is weighted least square. Why did we need weighted least square? Because we said that the noise variances are different. Okay. Now, if I can somehow make all the noise variances equal, or covariance matrix to be identity matrix, right? Then simple least square is enough. I don't need a weighted least square. So if I transform my data point, my yi is my resultant data point. This is what I observe. If I somehow transform a data point yi into some other data point, so it's that in the resultant domain, with the resultant data point, if I model the equation, a simple least square is sufficient. You don't need a weighted least square. That is basically the question. Okay, would anyone like to answer how to go about it? Okay, so let me just tell you. So in general, we perform simple least squares with uncorrelated noise entries. Therefore, first whiten the noise. So what should you do? Very simple. Go back to our third, second problem. This precisely whitening is first problem. Let y dash be defined as Cn, which is a noise covariance matrix, is defined as Cn power minus half times y. Okay. Therefore, pre-multiply by Cn power minus half on both sides to the equation y equal to ax plus n. So what do you get? You get Cn power minus half times y equal to Cn power minus half times ax plus Cn power minus half times n. Right? This is called y dash as per this equation. Let us call this effective matrix as a dash. This x will remain as x. This effective noise is n dash. But the property as n dash now is by problem 1. Expected value of n dash summation is what? What is this expected value? Yes. Yeah, it's identity matrix because this is exactly if you transform it, this multiply by this covariance Cn power minus half, that will make the effective noise to have a covariance matrix equal to identity matrix. Okay, that implies noise is uncorrelated. No, n dash noise is uncorrelated. Okay, therefore we have the system y dash equal to a dash x plus n dash with n dash uncorrelated. Now apply simple least square because we told uncorrelated noise, simple least square is enough. Therefore, by simple least squares, what is the x hat least square is nothing but a dash transpose a dash, the whole inverse a dash transpose y dash. That's all. Okay, where a dash equal to Cn power minus half into a and y dash equal to Cn power minus half into y. This is a transformed domain. Okay? Transformed domain. Okay, sanity check. Whether this is correct or not, let's do a sanity check. Okay, replace a n dash and y dash by their um, um, by these expressions. These expressions. So what do you get? So XLS is nothing but a dash is nothing but so transpose is a transpose. So okay, let me write down it again. No problem. A dash transpose a dash the whole inverse a dash transpose y dash, which is same as a dash transpose, right? That is same as Cn power minus transpose by 2 into a the whole transpose. Sorry. This is just half transpose into Cn power minus half into a the whole inverse Cn power minus half into a whole transpose into Cn power minus half into y. Okay, that you just simplify it a bit more. There's nothing but a transpose into Cn power minus half into Cn power minus half into a whole transpose whole inverse into into a transpose into Cn power minus half into Cn power minus half into y. This is nothing but a transpose Cn a the whole inverse a transpose Cn inverse y. Now you see, this is exactly weighted least squares solution with weight equal to Cn inverse. Okay. Now if you see, that is exactly how professor also defined his weight in the class. Take the diagonal matrix with all inverse variances. That is the inverse of the covariance matrix. That is what we have also gotten. So that means, but that means what is it? This solution, which is simple least square in the domain of having transformed by the matrix Cn power minus half, will boil down to a weighted least square with weight equal to Cn inverse in the actual domain. Okay, that is a sanity check. Fine. So this is a solution. So basically, it's possible to view a weighted least square as a simple least square problem if you if you basically view one particular vector in some other domain. You basically transform the domain in which you are representing the vector one. There's a question. Beamforming is also weighted least squares. Well, in some sense that's true. I mean, because yeah, that's true. In some sense that is true. Yeah, but let's not delve into that now. But yeah, you can view it like that. Fine. So now let's go to the next question. This is the fourth question of the day. Okay. Suppose I have yi equal to all are scalar numbers. Okay, yi is a scalar number equal to xi plus ni, where I ranges from 1, 2, 3, and so on, capital N. Okay, so all these are scalars. All are scalars. Okay. Now, in the class, professor mentioned one fact, right, that the MMSE estimate, suppose I get to observe y1, y2, and so on till yn. And if someone asks you what the question, what is the MMSE estimate of x? Then the answer is the conditional expectation of x given y. Okay. This question is, why is that the case? Why is the MMSE estimate of x equal to expected value of x given by? Why is it the conditional mean? Why, if I tell you that, if someone asks you MMSE, why is it that the answer for MMSE estimate is always a conditional mean? Okay, why is it that? We are going to see the solution for why is that the case. Okay, so just go back to the definition of what MMSE is. Well, first let's see MSE, not MMSE. MMSE is minimum mean square error. We'll say what is MSE, mean square error. Nothing but expectation of, that is the average. Expectation means average, right? Average of the quantity x minus x hat, where x hat is the estimate of x, right? But now note here, the actual variable which you're trying to estimate is what? X. This is a true value. X hat is an estimate. This is a true value. X hat is an estimated value from observation of x. See, I don't get to see x. I only get to see y, which is an observation of x. So from the observation y, you get x hat. This is an estimated value from observations. Okay. Now there are two important things to note here. Here, model x, right? The true value to be a random parameter. That is the Bayes. This is also called the Bayesian estimation. Okay, MMSE falls under the broad category of Bayesian method of estimation. So here model x to be a random parameter. Okay, that is basically random parameter means that is therefore random variable. Okay, with appropriate mean, with appropriate prior mean and variance. Okay, now this is the first source of randomness in the problem. The second source of randomness is also, why is random? What is a y? Observation is also a random variable because of two reasons. I mean, because it is obtained using two random variables. two random variables. What are those? Both x and ni. These x is the actual signal, which I assume to be random variable as per the first point. Ni is a noise that gets independently added to the system. That is another source of randomness. So there's a two reasons. X is a random, n is also random, and x and n are independent of each other. They are independent two independent random sources contributing to one observation y. So that's why y is also random variable. Okay. Therefore, your estimate, your x hat is only a function of y, right? You only get to see the total effect, that is yi, and you make a function of yi to get the estimate of x hat, right? Is also random because y is a random variable. The function of a random variable is also a random variable. So x hat is also a random variable, as it depends only on y, which is a random variable. Okay, so that means the averaging that you do in the MSc the expectation, that is the averaging which you do, should be done such that the averaging is done over all randomnesses in the system. Okay, so here therefore your MSc, which is your C, is nothing but expectation of x minus x hat square. Correct. Now, what are the two variables in the MSc? X and x hat, but both are random because that's what I told before. Xi assumed to be random. X hat is also random because y is random. Okay, so the averaging is taken over all sorts of randomnesses in the system. That is both x and x hat. It's a joint expectation. It's very important to understand. Okay, the expectation is taken over the distribution of both the random variables x and x hat. But in turn, x hat is a function of y. Okay, so this is also same as taking expectation over x and x hat of y. And you can write your x as x hat x minus x hat of y. Both are, it's x hat of y means a function of y. Okay, it's not x hat into y, it's x hat of y, which means for every y you will have a particular x hat. Okay, this is your MSc. Therefore, okay, now this you can write it as, okay, there's something called, again you can write it by some mathematical laws, by something called law of total expectation. Like how you have law of total probability, you condition on a probability and then you take sum over all such probabilities, right? Similarly, you can condition over expectation and you take an expectation over all such conditioned expectations. Okay, this is same as taking expectation over okay, before that let me tell you, this is same as taking expectation of x comma y, because x hat and y have one-to-one relationship. So averaging over all x hat will be equivalent to doing averaging over all y also, because they have one-to-one relation. Okay, x minus x hat of y. Okay, now by law of total expectations, you can write this expectation as first you take expectation over x. Okay, that is you average over only all x, randomness in x. Okay, times x minus x hat. Okay, you will get all averaged over x only, but x hat is still random or y is still random. So this is nothing but this averaging is over only x. So that means given y equal to some y, you average over all x and then take a final averaging over y. Okay? So this is basically called the law of total expectations. Therefore, now I need to minimize C. That is an MMSE problem. Okay. So this C is nothing but MSC. Minimize C is nothing but MMSC. Okay. Now minimizing minimum C is obtained if the inner term is also minimum. Which is the inner term I'm talking? I'll highlight. Inner term in above is also minimum. That is, I'm basically referring to this is the inner term. That's because if I minimize all the inner quantities, and the average of all small quantities again going to be a small number. That's it. Okay. So minimizing the entire full number is same as minimizing all the inner numbers, inner term numbers. Okay. So therefore, we have the problem minimize with respect to x hat. I need to find x hat such that expectation over x, which is the inner term of x minus x hat of y, square given y, because this inner term is conditioned on your observation y. Conditioned on what observation you have seen. Okay. Or basically, if you want, you confuse, this is equal to small y for all small y. So this is same as saying, just compactly I can write this as minimize with respect to x hat expectation of x minus x hat of y whole square given just capital Y. No need to write equal to small y because it holds for every small y. So just given capital Y. Okay. So for that, let me expand this. This is same as minimization with respect to x hat. Let me denote the C as C in because it's the inner term. C in is equal to expectation of with respect to x minus x hat of with a function of y whole square given y. Okay, this is nothing but just expand the square term. This is the expectation of x into of x square plus x hat square of y minus 2 into x hat of y given y. Let me just take some space. Just a minute. X square plus x hat of y square minus 2x hat of y given y. Okay. Now do basically this should be equal to 0. I mean, sorry. If I want to minimize C in, therefore d by dx hat of C in should be equal to 0 for minimum. That's what we know, right? For minimum, you need to differentiate and equal to 0. Okay, and why should I should differentiate with respect to x hat? Because that is what I want to find the x hat at which the minimum is attained. So I need a differentiate with respect to x hat. Okay, that is same as saying dc by dx hat of y is nothing but d by dx hat of y into expectation of x with respect to x square. I'm just copying from our x square plus x hat of y square minus 2x x hat of y given y. Okay. Now I'm gonna make an assumption which is not incorrect. You can always make this under if this condition is satisfied. Okay. Assume that differentiation and expectation can be interchanged. For practical purposes, this is always true. Okay. Differentiation and expectation can be interchanged. That is, interchange means, okay, I'll tell you what does it mean. You can write your, that is d by dx hat of expectation with respect to x hat. I can write this as expectation with respect to d by dx hat of x hat. That is what I've told. Okay. Assume that you can swap the order of operations because d by dx is an operator. Expectation is an operator. So you have a cascade of operators. I'm saying that you can interchange the order of the operators. Okay. Of course, mathematically, this requires you to prove certain theorems. For example, there's something called dominant convergence theorem. There's something called monotone convergence theorem. You need to, they basically give you the conditions under which you can interchange expectation and differentiation. But for the purpose of now, practical purposes, they hold true. So you can do that. Okay. So then what you get is basically 0, but this should be equal to 0. This differential will be equal to 0. So I'm just going to do the 0 equal to expectation with respect to x times d by dx hat of y times x square plus d by dx hat of y into x hat square of y minus d by dx hat of y into 2 into x hat of y given y is equal to 0. Okay, this is nothing but see differential with respect to x hat of x square. This x square is a constant with respect to x hat. So this is nothing but expectation of x with respect to 0. This is nothing but plus 2 into x hat of y. So minus 2x into minus 2x because with respect to x hat, x is a constant. Okay, so just differentiate with respect to x hat. And it's not just that, it's just given y equal to 0. What does it mean? Expectation of x with respect to 2x hat of y minus 2x given y equal to 0, or by linearity of expectation, the same as expectation of x hat of y minus given y equal to expectation of x given y. But you see, given y, your x hat of y is a constant because conditioned on y, your x hat of y is a deterministic quantity. So expectation of a deterministic quantity is same as the deterministic quantity. Conditioned on y, x hat of y is fixed. That is deterministic. There's nothing random about it. So therefore, the expectation is equal to the expectation of that number is same as the number itself implies x hat of y is nothing but expectation with respect to x of x given y, which is nothing but the conditional mean. And the x hat, how did you obtain? By minimizing the mean square. That is why this is called MMSE. This is the MMSE estimate. That's why the MMSE estimate is always given by the conditional mean. Okay, so this is very important. Even if you do channel estimation for wireless communication, right? It's a very handy tool. All it says is there should be two random variables which will be involved. One will be numerator, another will be the conditioning event. The conditioning random variable will be the random variable corresponding to the observation. The actual random variable which you're taking in the numerator will be the random variable pertaining to the parameter which you want to estimate. You just take the conditional expectation that will define the estimate of the parameter that you want to estimate. Okay, so all you do is in several applications that you find, channel estimation or wireless communications or data detection or whatever application you have, all you need to identify is what is the observation and what am I interested in. If you identify these both, you will be able to compute the expected value of x given y. Okay, in fact, okay, all our LMMSE estimator, if you remember from previous sessions, or you can, all those expressions are derived using expected value of x given y. Why? You go back to our original notes here. Let me just scroll up. You see here. You see here. You see here. For example, if h I want to estimate and I'm given y, what is see the expression for conditional expectation? RHY times RY inverse MY. This is nothing but your LMMSE estimation also. Go back to your previous notes and you can see that they are nothing but LMMSE estimation. That's why conditional expectation is very simple to compute, especially if the distribution is Gaussian distribution. Okay, so there's a chart question. There's a chart question. Solve example. I think all the examples, all the problems that we have solved in the pertaining to estimation theory in the previous sessions will all fall under the category of this conditional expectation. Okay, but nonetheless, I also have some problems now to solve. Okay, we will solve that now. Okay, we will now solve the problem that goes as follows. This is question 5 for today. Okay. Just a minute, let me check. Fine, let me solve this. So in fitting a line, is line fitting like regression problem. We all remember it, regression. In fitting a line through experimental data, we assume the model x of n equal to a plus bn plus wn n. Okay, where n ranges from minus m to plus m. Okay, where w of n is the white Gaussian noise with variance sigma square. If we have some prior knowledge of, see, b is like the slope of the curve xn, and a is like the intercept of the line xn, right? It's like we model the equation y equal to mx plus c, but in addition there's a noise term here. That's the only difference. You want to model the line. I'm fitting a line. So basically there are a lot of data points, and I want to fit an approximate line through the data points, and I want to model this line as x of n, which is like a y equal to mx plus c, which is like a bn plus a, plus some noise. You add some noise because always any observation will come with noise. If you have some prior knowledge of the slope b and intercept a, such as your a and b is a vector, it is distributed as a prior distribution, as normal distribution, it is Gaussian distribution with mean a naught and b naught, and covariance matrix sigma square a, see, 0, 0, and sigma square b. Right? Question is, find the MMSE estimator of A and B, okay, as well as the minimum MMSE. That is, you find the estimator of A and B, and also the error involved in estimating them. Okay, assume A and B are independent of W of n. That is, they are independent of noise. They are independent of W of n. Okay. Then the question is, which parameter among A and B will benefit the most from the prior knowledge? Okay. I'll explain this question as we solve this problem, but let's first solve the problem of finding the MMSE estimator of A and B. Okay, for example, this is a line fitting that I want to do, and I'm interested in finding what is the slope and the intercept of this approximate line that I'm trying to fit. Okay, but someone a priori told that the slope and the intercept has a prior distribution. This is also called the prior distribution. Okay, the prior distribution of a Gaussian distribution with mean as a naught and b naught, and the covariance matrix as sigma square a 0, 0, sigma square b. Here's a question. Let's first do this. Then we'll worry about the second part of question. Solution. Now we can, so the see the m, see the for every n, for every n you have an equation. Then how many m such n are there? It ranges from minus m to plus m. That is, you have 2m plus 1 equations. Okay, you have 2m plus 1 equations. Stack all of them as a vector in a matrix form. Okay, we can write the system of observations as x of minus n, x of minus m plus 1, and at some point you get x of 0, and at some point you have x of m. Okay, so this guy is a 2m plus 1 vector. Okay, cross 1, which is equal to 1, 1, and so on till 1, minus m plus 1, and so on till 0, and so on till m, which is something but 2m plus 1 cross 2, times AB plus W of minus M, W of minus M plus 1, and so on till W of 0, and so on till W of M. Okay, so this is again 2m plus 1 cross 1. Now you see, for example, you take the first equation, x of minus m is nothing but 1 times a plus minus m times b plus w of minus m, which is same as this equation, x of minus m equal to a plus b times w minus m plus w of minus m. For example, you take the last equation, x of m equal to 1 times a plus m times b plus w of m, which is same here, x of m equal to a times a plus w times m plus w of b times m plus w of m. Right. So basically, you have represented this equation for all the 2m plus 1 observations in this compact matrix vector multiplication form. Okay. So this is now of the form. The above equation is of the form x equal to h theta plus w. Okay, where basically this is x, this is your h matrix, this is your theta vector, and this is your w vector. Okay, and given x, we have to estimate theta. Because theta contains a and b, we need both a and b. Okay, so that is basically you have represented in compact form. Okay, so now if you basically, the question is then find theta, we have to estimate theta in using in MMSE approach. Okay, this is also what is called the linear model, for which professor had given the solution in class. Okay, so for example, similar to this, let me go back to that that point. Yes, like this. You see here, similar to this expression. Here, the only difference is this h hat was a scalar. Okay, see this function. Given y equal to a xh plus b, where h is a scalar, I want to find MSE of h given a vector y. That is what professor did in class. This is also linear model. Okay, but now the difference is in the present problem. The difference is, given a vector x, I need to estimate another vector theta. That is the only difference. The parameter which I want to estimate is now a vector. Okay, I'm giving a ready-made equation. If you compute, so what should you do? Therefore, compute expected value of what? What given what? Tell me now. Conditional mean, because I'm interested in theta equal to theta hat MSE. Tell me what is expected value of what given what? Yes. Is it x given theta or theta given x? Because you only x is something that you can always observe. That means you can only given x, given your observation is x, not theta. Given your observation x, what is the expected average value of your parameter theta? So it is theta given x, not x given theta. Okay, so you need to compute the conditional expectation of theta given x, and that will be your theta MMSE. Okay, so basically we need to find out. See, we need to figure. I know the distribution of theta. It is given in the question. Theta, basically this is our theta, right? Is given by this Gaussian distribution. Fine. I know. So basically your model is such that x is equal to h theta plus w. H is a deterministic matrix. Fine. Theta is a random vector. I know the distribution of theta. W is also a random vector because it's noise. I know the variance and mean. So that also I know. I can find out the PDF, the probability distribution of x. Okay, so if I know the distribution of x, if I know the distribution of theta, I can find the conditional distribution of theta given x, which is same as what professor did in class. And then I need to find the expected value of that distribution, and I'm going to give you the closed form expression up front. Okay, I'll give you the reference. So I'll give you the reference for this text, reference text for this problem. So it is the fundamentals of statistical signal processing. Okay, specifically estimation theory. Okay, this is a book written by a very esteemed professor. It's by Professor Stephen K. He's now a retired professor. He's an American professor. This book is a very good reference text for understanding estimation theory. Okay, so from this text, I'm going to give you the exact value for theta MMSE for a linear model x equal to h theta plus w. So theta MMSE is given as mu theta, that is the mean of theta, plus c theta inverse plus h transpose cw inverse h the whole inverse h transpose cw inverse times x minus h mu theta. Okay, where we should tell now what are these variables. Mu theta is the mean of prior distribution. Okay, c theta is a covariance of prior distribution. H is already known. This is your H. This is the H. Okay, then CW, your covariance of noise. Then everything is done. X is your observation. Everything else is known. Okay, here specifically your mu theta is nothing but A naught and B naught, because that is what is given, right? See, normal with mean A naught and B naught. That is expected value of theta. What is your C theta? Is given as sigma square A 0 0 sigma square B. What is your CW? Sigma square I, because every noise is identically distributed with noise variance. Where is it given? Sigma square sigma square. Okay, so you have all the expressions. Just substitute in this above expression and get the MSE. Okay, so let's do one by one. Let's first compute this inner term. This is first term. Okay, let's compute the first term. H transpose what? CW inverse H. CW inverse H, which is same as, but CW inverse nothing but 1 by sigma square some identity. So the same as 1 by sigma square H transpose H. You can show that your H is nothing but this matrix, right? This matrix your H. So your H matrix is given by 1 by sigma square times 2m plus 1, 0. You can show this, okay? I'm just multiplying. I've done it already, so I'm just showing it here. Summation n equal to minus m to plus m n square. Okay. Therefore, the next is this guy. This guy is your second term. Second term is nothing but c theta inverse plus a c theta inverse plus h transpose cw inverse h the whole inverse, right? This is what we in a compute. You can show that this is given by your c theta is given by 1 by sigma square a plus your this matrix is nothing but your 1. So this is just given by this matrix. This is same as n by or 2m plus 1 by sigma square 0 0 and 1 by sigma square b plus summation over n square by sigma square the whole inverse. This is nothing but 1 by sigma square a plus 2m plus 1 by sigma squared 0 0, and you have 1 by sigma square b plus summation over n squared divided by sigma square. Okay. Next is what? I need to compute. This is a third term. Let's compute the third term now. Maybe this color. This is a third term. Third term. Nothing but what is it? H transpose C inverse, right? H transpose CW inverse times X minus H mu theta is same as 1 by sigma square, because C in W inverse something but 1 by sigma square is some identity. So 1 by sigma square times H transpose X minus H transpose H mu theta. Okay, but H transpose H is nothing but we saw above, right? That it's 2m plus 1, 0, 0 summation over n square. Therefore, you can show that H transpose CW inverse times X minus H mu theta equal to this number 1 by sigma squared times summation over X of n from n equal to minus m to plus m minus n times a naught, and summation over n equal to minus m to plus m x of n into x of n minus summation over n equal to minus m to plus m n square b naught. Okay, so basically what I did is basically you have H transpose H, you know H transpose, you know X is just X of n, and mu theta, you know A naught and B naught. Just put all of these, substitute these values in the expression and find out this. That's what I've written it here. Therefore, using all of these expressions, okay, basically I've computed term by term. I'm going to now write down the total expression theta hat MMSC equal to A hat and B hat is nothing but A naught plus 1 by sigma squared times summation over xn minus n times A naught divided by 1 by sigma square A plus n by sigma square. Sorry, this 2m plus 1. 2m plus 1 by sigma square. Here n is nothing but 2m plus 1. Okay, 2m plus 1. N equal to minus m to plus m. And b hat is given by b naught plus 1 by sigma square times summation over n into x of n minus summation over n square into b naught, the whole divided by 1 by sigma square b plus summation over n square by sigma square. Okay, so I will basically directly give you, so this is the expression for A hat and B hat. Okay, now if you ask me the MSC in A hat, that is the other part, right? MSC in A hat is nothing but you can show that is given by C theta inverse plus H transpose C inverse H the whole inverse. This is a matrix. Take the 1 comma 1th element of that. That is the MMSE of A hat. You can show that this grows as 1 by sigma square A plus 2m plus 1 by sigma square the whole inverse. You can show. Similarly, MSE in B hat, which is your minimum, the mean square error in estimating B is given by C theta inverse plus H transpose CW inverse H, the whole inverse of the 2 comma 2th element. Can show that this is nothing but 1 by sigma square B plus m into m plus 1 into 2m plus 1 by 3 sigma square the whole inverse. You can show that these are the answers. Now, okay, so we have done. Okay, what is the grade? Okay, this is basically the MSC and the theta hat estimate. This is for A hat. This is for B hat. MSC is this. MSC of A hat is this. MSC of B hat is okay. Fine. What is so great about it? Now comes the very important aspect. You see here, the next part of question asked, which parameter among A and B will most benefit from the prior knowledge? Okay, so basically prior knowledge is something that will help you to estimate the parameter with whenever other parameters in the system are not helping you much. Okay, for example, you see this expression m, the number capital M denotes the number of data points in some sense, like it's 2m plus 1. So if m increases, the data points also increase. If you see the MSE in B hat, if M increases, okay, both MSE of A hat also decreases and MSE of B hat also decreases. That is, error in estimating A hat decreases, error in estimating B hat also decreases. But if you see in B hat, M appears something like M cube, okay, but in A hat, M appears only as M. So the decrement in the MSE for B hat as a function of M is much more than the decrement in the error for A hat. That is, if I increase the data points, then I can estimate B hat much better than what I can estimate A hat. In other words, if my data points are not so large, then my A hat will be most benefited only from the prior compared to what the benefit B hat's MSE can get from its own prior. Okay, therefore, since as M that is a number of data points, okay, that is a number of data points increases, MSE in B hat decreases much more than MSE in A hat. Therefore, A hat benefits more from the prior. Okay. Okay. Fine. So these are the questions that I wanted to solve. Okay. So another one important announcement that I would like to make is, so we have finished 12 regular TA sessions by today. We will have one more final TA session where I will walk through research problems and also summarize this course. With that research problem, I will be able to summarize the course this coming Friday. Okay, you will also get a formal announcement from the NPTEL side, but I'm also informing from my side. The coming Friday between 6 and 8 p.m. we will have the final TA session for this course. So please attend without fail. Okay, that will be the concluding TA session for this course. Okay, so before we wrap up, are there any questions in this in today's session? I think SVD and PCA by example relationship. I think this we have seen long back in one of our TA sessions also. I think Professor had also mentioned about it. You can just take a look at that particular lecture, and I think that will clarify the doubts. Okay, so let me stop recording.